Thank you, everyone, and welcome back. We are now ready to kick off again with a new bulk of presentations. First presentation now will be Therese Rannem and Hilde Tveit Haaland. Therese from Neptune Energy Norway and Hilde from Cegal. That will talk a bit around machine learning and how you can use that for facies classification. So please, Hilde and Therese, go ahead.
Yes, thanks, Stoffe. So again, my name is Hilde Haaland, Senior Geophysicist Data Scientist with Cegal, and I'll be presenting this machine learning-driven facies classification talk together with Therese Rannem from Neptune Energy, and she's going to do a quick introduction, both of herself and of this talk. So I'll leave the words to Therese for a few minutes.
Okay, thank you, Hilde. So, yeah, my name is Therese Rannem. I'm the Digital Subsurface Manager in Neptune. We've had our digital initiative in subsurface going on for a year now, and we've been working with Cegal very closely. They have been providing us with the data scientists and developers, and it's been a really nice experience so far. So here we're going to talk about one of the use cases that we've developed together. We've been always kind of having this idea that we wanted to solve pain points that we have in the subsurface workflows. We've been looking at what things that take a long time today that we could find solutions for. So one of the things that came up after we had an intro in Python was that can we make something that make these lithofacies classification faster? So yeah, because our company has different offices around the world, and of course there isn't one way of doing it. So if we could just find one way to give to the whole company, that would be a value. Yeah, as we have on the slide here, a lot of times when we are drilling, our management wants results fast. So that's really the use case. When we're drilling, we get the logs and we can just try to interpret the facies faster than we do today. So then I'll leave it to Hilde to do the details and say more about how we went on with this.
Thanks, Therese. Yeah, I'll take the presentation forward. So I'll just skip to the next slide here. So yeah, so as Therese said, lithofacies interpretation was identified as one of these pain points in Neptune's workflow. So we had a geologist from a specific field, who had kind of the initial idea or the initial want for an easier solution to be able to kind of roll out lithofacies interpretation quicker. So this specific field, they had some exploration wells and they were having a well campaign later in the year, and they wanted to assure that they would have kind of a quick turnaround of raw well data to lithofacies interpretation, both for management and for feeding into their geo models kind of during their drilling campaign. So to minimize the time from wells drilled to geo models being fed this new interpretation, it was decided to test a machine learning driven approach for this lithofacies classification. So I mean, if many of you or any of you have done a bit of lithology interpretation, I mean, it's generally a manual task. It can be time consuming. And if we think about, you know, how we would perform that task, we have a lot of well information. We try to consider, you know, log responses from plenty of different well logs. and make a good and consistent interpretation. In general, we can say that, or in general, it turns out that as humans, we have the ability of thinking approximately in 3 dimensions. Maybe Magnus Carlsen can think in 4. But for most of us, we're generally confined to 3 dimensions. And when we're thinking of interpreting lithology, we're generally looking in quite a lot more than 3 dimensions. And that's a bit of a problem. That leaves us to kind of trying to have good workflows to assure that we're being consistent. But it's difficult to assert that at all times. So instead of kind of having this geologist spending a lot of time trying to interpret these logs manually and consistently, we aimed to build a classifier from one of the discovery wells and then be able to apply that to the future wells coming in to assure that all of the good work that kind of went into interpreting this first well was utilized when the next wells came in. So this would alleviate the time-consuming part of the lithology interpretation and free our geologist's time, so she could spend that QCing those automatically interpreted logs before feeding them into the geomodel. So we're containing the knowledge of the geologist. The geologist would still evaluate the output of this, but she would not have to spend so much time doing the manual labor to get these lithology or lithofacies interpretations generated. And then obviously a very good kind of secondary aspect of this is that you have a quantitative way of handling the uncertainty in your interpretation. So as I'll show a bit later in this talk, we, in addition to creating a lithofacies interpretation, we also create or output probabilities of each interpreted lithofacies. So you can actually have a quantitative measure of how certain you are that the lithology that you have interpreted for a specific section of your log is that lithology, and which other lithologies it competes against, depending on your logic of interpretation. So for this project, we needed to think about what type of technology we wanted to use. So we needed to land a tech stack that would fit the project at hand. So I mean, the first thing you would think about is who is the end user. As Therese mentioned, I mean, this was this came out of this digital subsurface initiative, and we were basically Python coders who were going to build this solution out. So it was logical that this would be a Python tool. So then we need to think about the Python competence of the end user. So we kind of quickly landed on, we would use, we're talking about relatively small data sets, so we would stick with scikit-learn and XGBoost as our kind of classifier algorithms that we would test, and we would use SHAP to evaluate our classifications. But what does that mean to this end user who's not necessarily a Pythonista and doesn't necessarily know how to both interact with Python code and understand both input and output in this process? So from that we had 2 delivery options to decide between. The first option that we initially intended to go for was to present Jupyter notebooks with a preset workflow where you would select your input data, run a workflow in the notebook. You could then go in and change whatever parameters you wanted to change in the code and have an output. We quickly realized, however, when we were kind of doing some user feedback and testing kind of during this project, that we should perhaps lean towards creating an app-based interface for our users to work with. The benefit of that as well would be that you didn't necessarily need to know any Python to use this tool. And we would open it up for not only the users who knew a little bit of Python or wanted to learn more Python, but we would open it up to kind of the whole base of geologists wanting to kind of try a new workflow for lithofacies interpretation. So that's really what we ended up with, an app-based interface. So we decided to build a web app based on a web app framework called Streamlit. And Streamlit is just a kind of a wrapper around it's basically a Flask setup for those who are familiar with building web apps in Python. But it's kind of nicely wrapped up, so it's pretty much like out of the box easy build web app API. So we used Streamlit to build the actual app, and we then used scikit-learn as kind of our machine learning library that we built the specific Python modules on. So the deliverables from the project would then be both the app and a set of Python modules that we could run in any IDE. Also, a notebook environment like the initial idea was. But then also as kind of the motor for this web app. Using web apps instead of creating or writing a desktop application is also nice, because you can you can host them locally, just like a desktop application. I'll do that later on when I show what we're the app quickly. But it also allows you to host it on a cloud, or for example on a Kubernetes cluster, like we showed earlier with Cegal Labs. And it's also easy to update it. So if we create some updates to our Python modules and we just rerun the code, you have an updated app. And by using a kind of preset app framework like Streamlit, we significantly reduce the development time of the app. I think it was 2 days to have kind of a functioning prototype of the app when we tested it out. Of course, it took a bit longer to have a nicely working app, but I mean, you can prototype a whole app in a matter of a day, or yeah. So it's a very nice framework to use. Quick throwback to those who saw my talk on Cegal Data Labs and Innovation Space earlier. So the idea when I mentioned that we could authenticate apps using Keystone, we haven't done that actually for this specific project, but this app that I'm going to show you later would be a perfect example for an app that could be hosted using this Keystone authentication system. And then you can just, you set whoever users you want to use it, and then they can access and use the app. The next thing we needed to do was to map out the app workflow. So I'll go through this a little quickly, because it's maybe not the most interesting for most of you. But in kind of wide terms, we have some sort of database where we collect our data from, and then we write data back to that same database. And what you want to do, or what we wanted to do, is that we wanted to collect our well, our type well, from this database, and then build something from the lithology interpretations that we had available. So for this type well that we had an interpretation by the geologist, the field geologist. We had a third-party interpretation that they gotten from a vendor. So that was kind of like our starting point. We also realized when we were going through this that it would be nice to have an option for when you do not have a lithology interpretation present at all. So we also added a clustering step where we could just input well logs from the type well and have a clustered lithofacies model that could then be input into this classifier build. So that's this option here. So we take the data, we evaluate it, we mitigate missing data, we splice logs, etc. If we're happy with the lithology interpretations that are present, we go forward. If not, we create this clustered fascist model. When we're happy with this step, we go into this training the classifier step. So we'll go more into this in detail later as well. But training a classifier basically just means that you build a way to get from some sort of input to some sort of output. So our output would then be the interpreted lithofasces, and our input would be the well logs. So you train this classifier on whichever input you choose of the 3 available. You analyze it, you look at how well the model performs. If you're happy, you can kind of move forward. If you're not, you can go back to data handling, handle your data, do whatever you want to try and mitigate the problems that you see occurring in your classifier, and train it again. So this is an iterative phase where you try to optimize your classifier as much as possible. Once you have a classifier that you're happy with, you generate the Fascies log, and this is kind of where your geologist comes back in with specific geology knowledge. So the geologist would then inspect both visually, but also, I mean, you can have a lot of different outputs here, both quantitative and qualitative, to evaluate how well that generated Fascies log is. When you are happy with it, you push it back out to your file system. If you're not happy, you can push it back up to another or an earlier part stage in the workflow. I'll show super quickly how the app looks, just to give an overview, and then we'll step into the app shortly. So this is the setup of the app that we wrote in Streamlit. You get to a welcome page, and then you basically just step through the workflow steps that you need to take to get to an output. So you build a k-means lithofasces log, you select your inputs, you select the parameters of your k-means clustering, and from that you can build that lithofasces log. If you have a nice lithofasces log, you would skip this step and go straight to creating a classifier. Here you can see an example of the output lithofasces log from this clustering in this example. Then once you've built that lithofasces log or decided on which one you want to use, we get to this build a classifier from type well. And this is really the point where we wanted to focus our efforts in this project. So we will be presenting a geologist with a machine learning model. We don't know how much the geologist knows about the machine learning. Probably not that much. Many geologists don't have that much experience using machine learning. So we wanted to democratize machine learning as much as possible. We didn't want to hand out a model that they don't know how works and then just say go for it, get a result and then trust that. So we wanted to spend a lot of time building good evaluation resources for the models that you then build. So we have some kind of standard ways of scoring a classifier, basically just seeing, how many samples am I predicting the correct lithology for in this classifier, and how many am I not. So we can see that this classifier scores fairly high for its training score, 98%. That's really good. Then we also created some more intuitive plots that a geologist would probably feel more comfortable using. So we looked at feature importance. Now our features would be the well logs that we input to this process. So each log would be a feature. So then we plot out by feature and by classified lithology, which feature kind of decided that this, or decides when this lithology is classified. So we can see that for shale, actually row B is kind of driving it. That's a bit strange. We would maybe have expected gamma ray to be more involved here. We can see that for sand, gamma ray is the main driver. Cemented sand compared to sand, gamma ray is the lower driver, and then row B and neutron porosity kind of picks up the slack. So that's a nice way to kind of combine your geological knowledge with the outputs of this machine learning algorithm or classifier. We also have a lithology confusion matrix. So this is basically predicted lithology against predicted lithology and how often for each lithology you predict correctly. And then you can also see what lithology do I confuse each lithology with. So you can see that for shale, in 98% of the time you get it correct, but you're sometimes confusing it with cemented sand. That's a safer result than if you would be confusing it with sand. The cemented sand log response is closer to shale than sand. So that kind of gives us a bit of confidence. For sand, we can see that we generally predict sand, but we sometimes predict cemented sand. That's also kind of a good sign that this classifier is working as we expected. And in that way, you kind of build up the confidence that this model is doing something that you want it to do. So I'll just quickly step into a demo, and I think I'm running a little short on time, so we'll do this very quickly. As I mentioned, an easy way of kind of deploying this would be to deploy it kind of through this portal with the Keystone Authentication, for instance. Right now, I'll just launch it locally from my desktop. So I have a shortcut here, and then I'm just launching a locally hosted web app. So there it is. I'll run through a very quick workflow here where we'll load a well. So I'll load an input well, and then we'll get some options here for what we can do. So we'll create a k-means lithofasces log from some input. I'll select the gamma ray, density, and porosity. And then I can set the number of lithologies that I would like to predict. I'm going to set 3 just to make it easy. And then I've cheated a little bit, like Ingrid Espik Håvik, so I know my depths where I have interesting reservoir lithology. So I'll set my minimum depth and my maximum depth to something logical for my well, and I'll click Generate K-means. So when this runs, I can see I have an interpretation here. This is the output lithofasces interpretation from this workflow. So I have three lithologies. I have something here. I can go up a little bit so we see the log types. This I feel fairly confident is a sand. And I can see I have a slight shift here, both in my density and my neutron porosity log, which is being picked up. And then up here I have a shale. So I'd say generally I have 2 sands and a shale. So I can see that my cluster 1 is a shale, cluster 0 is a good sand, and cluster 2 is maybe a cemented sand. So what we'll do is that first of all I can download this k-means log by creating a link and clicking that. Then I have it downloaded here. It just saves nicely in my downloads on my computer. But so what I want to do now is that I want to define what these cluster values are. So cluster 1 doesn't really tell me anything. I know it's shale, so I'll define it as shale. So I'll go down here and define lithologies. I'll set this as shale, and I'll select a nice color. I'll do green. That's generally what I do for shale. Once that's run, I have bad memory, so I'll go back up and I'll see that my good sand is cluster 0, and then my cemented sand is cluster 2. So we'll write that in here, sand. And then cemented sand. Give that a nice cyan color. So once that's set, I can download this lithology description. I'll need that when I want to run this this classification later. So I'll download that again, and again it just saves in my downloads folder. From here I can build a classifier. So this is actually where we kind of step into this. Here we can use the information that we've now gathered from one well, and then apply that to other wells using this classifier that we're now going to build. I'm just going to pick the same logs that we used to build this k-means classifier, the k-means clustering above. But here I could use, say I had 10 great well logs that I wanted to use or 10 like good quality logs that I wanted to use to interpret my lithology in the first step. And I knew that I would only have, five logs that I would want to use to classify or to interpret lithology in my next wells. I could then build the first initial lithology log using all the input wells, and I could build this classifier from that lithology log using the fewer wells. And then hopefully I would kind of save, or I would pick up a bit of the information that I'm missing out on from those 5 then missing wells from my next logs from my next wells in this classifier. I'll select, this is the one that we created above, the generated k-means with 3 clusters. And then I'm just going to leave this test train split as it is. That's basically just defines how much data I hold back for testing the performance of my algorithm. So I'll let this run. This takes a little bit of time. How am I doing on time, Stefan? Yep. So what is actually happening right now is that the algorithm is training. Basically, we selected a random forest classifier here. We could have we have a few other options. But what we're doing is that we're building a decision tree using these 3 logs as input. And then I'm trying to build a good, or I'm building plenty of decision trees really. And then I'm averaging those decision trees to try to get a good result that matches this generated k-means 3 lithology interpretation. So here my classifier has been trained. And if I scroll down, this is where I get to these scores for my classifier that we were looking at in the presentation. So we also added quite a lot of explanations here for how to kind of use the different tabs, how to read and understand these scores. And that, I mean, that's kind of to give this tool back to the geologists so that they can trust the result that comes out, even though they don't necessarily understand the full concept behind what we're actually doing now. So we can see we have a fairly good classification score both for our trained data and our test data. You want these to be high and fairly similar. It's basically just testing your algorithm on both the data set assigned to train and the data set assigned to test. Our log loss score, we would want to be as close to 0 as possible. So we're doing quite a good job here. And then when we're getting down to this confusion matrix and feature importance, we can see that we're also getting fairly consistent and good scores. If we want to look at what drives each Facies interpretation, we can see cemented sand, density, and neutron porosity drives it mainly. Shale, neutron porosity, and gamma ray, sand, gamma ray, and density. Maybe not what we would have expected, so we might need to take like a quick look at this model again. But for now, we'll just download the train classifier, and then for my last minute, I'll apply it to a well here. So I'll skip to the next tab here, and then I'll select a new input well, which is my output well. I'll select a pickled classifier. And I need to go to my downloads. Where is that? So I'll select the one that we just built, and I'll select my lithology description. So that's this one here. Like that. Okay. Then I can view my input log. So this is a new well. So I'll grab the same logs that we had previously. And then I'll just plot that. Yeah, so we can see we have same logs available. So then we can apply this classifier. Here, in this classifier pickle that we've saved out, we've also saved out what features the classifier needs to run. And then we try to match these logs with logs available in the new well. If there wasn't a name to name or like a identical name match for a GR, we could use the drop-down list and select the matching well. And you would also be kind of prompted to do that before you can continue. Luckily here, all the wells have the same name, so we can just continue to apply classification. Here we can also just, because we know we're only looking at a reservoir section, I'll just set this to the reservoir section of this second well. And then we'll apply this classifier to the new well. And this is quite, this isn't very time consuming compared to training the classifier. But so this is our output, and we have our 3 lithologies predicted with the colors that we set for the prediction. So we can see that this is actually our good sand. This wasn't as yellow as I intended, but we don't have that much good sand. It's predicting quite a lot of cemented sand and some shale here. And then the power of this compared to when a geologist would do this interpretation itself is that we have these 3 logs here. So this is the probability of having lithofacies sand. So you can see a high or a very dark saturated color. It's a high probability of having sand. And then lower saturation colors, some probability of having sand, but lower. So you can see that shale definitely wins out here, but you do have some probability of having sand, no probability of having cemented sand. So in more complex settings, you can use this output to then evaluate whether or not you should be confident in this interpretation or not, or whether or not you should maybe create more scenarios in your modeling, or how handle it however you see fit as a geologist. If I'm happy with this, I can download this well, and then I'll just have a last file that I can load back into Petrel or wherever else I work. So that also just downloads here. I can open it, hopefully, if it doesn't take long. Yeah, so here I have a perfectly normal last file that I can just upload directly into Petrel. Yep, so then with that, I conclude the talk. This was a very nice kind of a quick to finish project where we could kind of very easily see, we're making an impact in a workflow, and we're doing it in a way where we use new methods that the geologist or the geoscientist might not be too familiar with, but we're trying to make it as familiar and as available knowledge-wise as we can for the geoscientists that would then work with this. So thanks for your attention, and if we have time for questions, we'll take them.
Yeah, I think we have maybe time for one question. It's about how did you calculate the lithology probabilities? How did you calculate the probabilities, the lithology probabilities?
Yeah, that's actually very, very simple. We used scikit-learn's implementation of in this example it was the random forest classifier that I showed. But when you output classification, it's generally it's the same as kind of building a regressor, and then you just take the class with the highest probability of being chosen and throw that out as your selected classification, or yeah, basically the classification of that point, right? So we, instead of just kind of capturing the most likely point, we also just output from that scikit-learn algorithm the probabilities of all facies. So that's just for those knowing scikit-learn, you can do predict and then input your data. If you write predict _ proba, then you get the probability of each predicted class, or each possible predicted class. Yeah.
Okay. Thank you very much, Hilde, and also Teresa from Neptune. Thank you very much for this contribution.